Hi everybody, in this lesson today we're going to be talking about vectors, and a lot of you have learned about vectors in your math classes before. We are going to draw on some of that information, but if you haven't learned about vectors in your math classes, that's okay, because it's really just going to be a matter of remembering Sohcahtoa and the Pythagorean Theorem. Let's first talk about vector addition. We will add vectors together, and so first of all, what is a vector? A vector can represent any vector quantity. So displacement is a vector quantity. There should be a comma there. Velocity, acceleration, force, anything that has both magnitude and direction. And we represent it with an arrow, and that's what I have over here. These are arrows that could represent vectors. The magnitude or size of a vector is shown by its length. And so make sure you draw it to scale, because if you don't, your answers can get a little confusing. If you do draw it to scale, you can kind of check off of your answer off of your diagram and make sure they look the same. And so it's helpful to draw it to scale. Okay, when we add or subtract vectors, which we will be doing quite a bit of in this class, here are some things you have to do. Always add vectors tip to tail. That means, like, if this vector, let's say, is vector A, and when I write a vector, I draw a little arrow over it to show that that's a vector. So vector A goes from here to here at this particular angle, and if I want to add to that vector B, it's going to go tip to tail, so that the tip of vector A touches the tail of vector B, and so forth. And then the arrowhead shows the direction of the vector. So that arrowhead is showing you, okay, it's going up and to the right, not down and to the left. Then we would connect those vectors, and we would call that the resultant vector. And so here I have my resultant vector. It's basically saying, okay, so you could have gone from here to here to here, or we could have just taken the shortcut and gone this way. And so that is the resultant vector. When you add two vectors together, the resultant vector is vector R. A negative vector, sometimes we have negative vectors, it's one with the same magnitude but opposite direction. It is a 180-degree difference. So for instance, anti-parallel. If you've ever heard that word before, that's what this is talking about. So here I have two examples. Let's say that vector, that's a really bad line, and this vector, they are anti-parallel because they are parallel to each other, but one's going this way, the other one's going that way, and so that causes them to be anti-parallel or negative vectors. And finally, so we talk about adding and subtracting up here, or adding vectors are talking up here. Here we're talking about subtracting. When you subtract vectors, it's just like adding the negative. And I don't like that arrow that I put in there. I think that should just be an equal sign. I think the arrow is making it confusing. So let's cross out that arrow and just say it equals. So we know that in math, 10 minus 3 is the same as 10 plus negative 3. Well, that's the same thing with your vectors. You can have a vector going here, and then add the opposite of it this way. That's like 10 plus negative 3, okay? Okay, like I said a second ago, you're going to need to remember to use Sohcahtoa. And if you don't remember what that stands for, that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. That's going to be very important throughout this course, but during this section in particular, but we're going to use it all year long. When you use the graphical method, that means like you're using graph paper and you're actually plotting it out on paper. You have to choose a convenient scale and choose a convenient coordinate axis. So like, do you want to say north, south, east, west, or 0, 90, 180, 270, or how are you going to label your axes? And so, or you could just have X and Y axes. And so that's when you're using graph paper. Sometimes it doesn't really make sense to use graph paper, or even if you do use graph paper, it's really helpful to now know some trigonometry, and that's what I'm talking about, Sohcahtoa. So when you do trigonometry, we have to break up our vectors into x and y components. And then we're going to add all the x components, all the y components, and then use the Pythagorean theorem to find the resultant. This is what I mean by breaking vectors into x and y components. Let's say you have a vector like this. Let's say that this vector is 10 meters long, and let's say that it is at a 30-degree angle. Well, then what we need to do is break this into components and say, okay, this is my this is my y component, and this is my x component of this vector. And then we're going to have to use some Sohcahtoa to figure out, okay, how long is x, how long is y? And so down here I have some space that we're going to set up some examples. This is example number 1, not example exclamation mark. So we're going to put example number 1 over here. Example number 2 is printed on the other side, but the graph paper is over here. So we're going to have to do some flipping back and forth if we have to. Okay, if you walk 25 meters north and then 15 meters west, what is your displacement from your starting position? Well, we have to set up a convenient scale. So just with the boxes that I have, it seems like if this was 10, 20, 30, and 40 meters, that would be an easy thing. As far as, it's big enough, but yet we can count that many, and we can say this is 10 meters, 20 meters, and we can say this is east, and this is 10 meters and 20 meters, and this is west. This, of course, is north. This would be south. Now, I'm using north, south, east, west because that's what's in the problem. Okay, then it says if you walk 25 meters north and then 15 meters west, what is your displacement from your starting position? Okay, I need to get a straight edge, so go ahead and get a straight edge. Okay, so I got my straight edge. I drew my first vector is going 25 meters north. My second vector is going 15 meters to the west. And so I drew those vectors. And now the question is, what is your displacement from your starting position? So we need to draw in what is the resultant vector that's going to be here. So again, I'm going to get a straight edge. I'm going to draw my resultant vector. Okay, so my resultant vector is this right here. I now need to do some math and figure out, okay, how long is that resultant vector? Well, I have not given any angles, but that's okay because I have enough information. I can just do the Pythagorean Theorem. All right, so I'm going to set up the Pythagorean Theorem. I'm going to take 25 squared plus 15 squared and set that equal to r squared. And on my calculator, 25 squared is 625, 15 squared is 225. I add those together at 850. And so then I need to take the square root of both sides and see what that comes out to. So the magnitude of the vector is 29.15 meters. And so again, if you have it on graph paper, you can kind of see, is that a realistic representation? If this is 25 and this is 15, then I think 29.15 seems about right because the hypotenuse should be longest side, and that is a little bit longer than 25. So that is my resultant vector. That's the magnitude. Now I have to find the degree, because here's the deal is when we talk about vectors, we have to say, okay, well, that might be the vector length, but then what angle is it going at? Because the degree, the angle, is an important part of the vector. And so I'm going to find this angle here. Now, I will say you could have found the angle down here. If you wanted to do that one instead, you certainly could have. I'm going to find this one just because it's already defined within the triangle, but you could find the other one also. It just matters when you explain it what you're going to call it. But if I use this one here, I have over here, I have a 15, right? It's 15 meters. And over here, this is 25 meters. And so I know that I'm going to have to use tangent. I know that the tangent of theta is 15 over 25, opposite over adjacent. But on my calculator, what I have to do to find theta is find the inverse tangent of 15 over 25. Make sure your calculator is in degree mode and just type in inverse tangent of 15 over 25 and see what you get. Okay, and I'm getting 31 degrees, 30.9, which is awfully close to 31 degrees. And I have to say what orientation. Remember I said you could have used down here, you could have used up here. So we're saying 31 degrees. 31 degrees where? Well, this is going to be new to you probably. We use this interesting language in physics. We say that that is 31 degrees west of north. Because straight north would be up this way. But we're not going straight north. We're going over a little bit, over to the west a little bit, and so it is west of north. If you had chosen this angle over here, and I'll just call this angle phi, if you had chosen this angle over here, you would have come up with 59 degrees, and you could have called it north of west. So we'll get some practice with it. I know it's new, a little bit different. Let's go ahead and turn the page and read the next problem. All right, example number 2. A plane flies 100 meters per second north with wind blowing at 28 meters to the southwest. What is the total velocity of the plane as seen from the ground? Okay, so we've got a couple things going on here. One is we have the plane flying at 100 meters per second north, and then we have a wind blowing at 28 meters per second to the southwest. Now, do you remember what I said a minute ago about north of west and west of south and all that different things? Well, if it says exactly southwest, that is a specific place, and that is the 45-degree angle southwest. Anything else could be a different angle, but if it just says plain old southwest or northwest or anything like that, it's going to be exactly 45 degrees. All right, but we need to figure out if it is blowing 28 meters per second to the southwest, what does that mean? So I'm going to go back to my diagram on the other side, my graph paper. So here I have drawn, and now I'm just using this little corner as like scratch paper. Okay, this is just my little scratch paper. Because save the rest of it, because we're going to do the rest of the problem on the big part. This is just a corner I'm using as scratch paper. So we have a 28 meter per second wind blowing to the southwest. That means that right here is a 45-degree angle. How long would each side be? Well, once again, we could do some Sohcahtoa to figure that out. Because I know that the sine of 45, and I'm going to call this one y, I'm going to call this one x. The sine of 45 is opposite over hypotenuse. That is y over 28 meters per second. And so what I could do is I could just say that 28 times the sine of 45 is equal to y. And so now I'm going to go into my calculator, and I'm going to just put that in my calculator and see what I come up with for y. And I'm going to round it, because what I'm getting is 19.7989897. So let's just call that 20. A couple things to notice. First of all, notice that this is a velocity. So when we draw our vector here, it's going to represent a velocity. Now over here, it was a distance. And so this is like literally like a map. But this one is not going to be literally like a map, because we're going to put our velocity vectors on there, not our displacement vectors. Okay, that's something. Another thing is that is 20 meters per second. So that means if this is 28 meters per second, then this side is 20 meters per second. And since it's a 45-degree angle, this side is also 20 meters per second. Let's go back to the problem. It says a plane flies at 100 meters per second north with a wind blowing at 28 meters per second to the southwest. What is the total velocity of the plane as seen from the ground? So one other thing we have happening here is what's going on as it's seen from the ground compared to what's going on actually in the sky. And so this is like a frame of reference. Like our reference point is going to be us on the ground, because the people on the plane might not see it that way, and even the captain might not see it that way. But let's stick with what the problem is. So let's draw a vector 100 meters per second north. Okay, this time, since I have a slightly different, something different going on, I'm going to call this 25 meters per second, 50 meters per second, 75 meters per second, and 100 meters per second. Now, if I do that, each one's like 5, right? 5, 10, 15, 20, 25, 25, 30, 35, 40, 45, 50, etc. So each little box is 5. That's important to note. Then, my initial vector that I'm talking about is the plane has an initial speed of 100 meters per second to the north. Then, it has this wind from there. It has this wind blowing at a 45-degree angle at 28 meters per second. And if that is true, then the y and the x are both 20. And remember I said 5, 10, 15, 20, we're counting by 5s. So that's going to go right there to 5 down here, so that now this is like 80 basically. And then 5 over here, actually 5, 10, 15, 20 over in this direction. So that is here. And the final question is, what is the resultant vector? What does it look like from the ground? And I'm going to call that the resultant vector. So I'm going to get out my straight edge, and I'm going to draw a line showing that resultant vector. Okay, here's my resultant vector. The plane is set to go, or thinks it's going, 100 meters per second north, but the wind is blowing at 28 meters per second southwest, and so it's slowing it down a little bit, right? Because the wind is blowing into the plane, and that should slow it down, and it's also going to blow it off course a bit. Now, don't worry, the modern electronics are able to account for that, so the captains are not going to have to do this in their head or get confused, but for our purposes, we're taking a look at what's happening. So now the question of how long is that resultant vector? Well, because this was 80 meters per second, because it took off the 20 and the 20, right? So now I just have this little triangle that I need to deal with. So this is the triangle that I need to find the distance, this r, the resultant vector. And for that, I'm going to use the Pythagorean Theorem. And for my sides of what I'm going to use for my calculating, it's going to be, look, it's 20 over here because of this 20 we calculated, and it's 80 over here because it was 100 minus 20. So I just need to take 80 squared plus 20 squared and find my resultant vector. So take a second right now with your calculator to find what that r, that resultant, is going to be. Okay, so when you do the Pythagorean Theorem, you should be coming up with 82.46 meters per second. Remember, this is a velocity vector. It is not a position vector. It is a velocity vector. So that's giving me the actual velocity that the plane is going as it appears from the ground. The next thing we need to know is, how about what is the angle? And so once again, we're going to look and figure out what is this theta. And so I'm going to go back to the inverse tangent like I was doing before. Opposite over adjacent would be 20 over 80. So I'm going to do the inverse tan. I'm going to come up with my degrees. And so when I do that on my calculator, I come up with 14 degrees west of north. In other words, it's about 14 degrees off course. If it thinks it's going north, it's actually not. The wind is blowing it 14 degrees off course. Which direction? To the west. It thinks it's going north. It's blowing it 14 degrees west of north. But again, like I said, the electronics on the airplane can calculate that, and you're not going to go off course if you are the passenger on that flight, because the captain knows what's going on, and mostly the electronics is doing it for them. But calculation-wise, vector-wise, that's how we would come up with it. Okay, we have one more example on the next page. Because this video is getting a little bit long, I think I'm going to stop here and we can do this example in class.